Welcome to the APL Quest. See APL Wiki for details. Today's quest is the fifth from the 2015 round of the APL problem solving competition. It's a straightforward problem of computing the standard deviation. Only little catch is that it has to work on an array of any rank, not just a simple vector. Now, I didn't have the pleasure to work together with Ken Iverson, but I did have the pleasure of working with his close student, Roger Huey. And Roger Huey used to say, "What would Ken do?" I can say, "What would Roger do?" And while I can't be sure, of course, I have seen Roger Huey write some tacit code, and I think this is how he would do it. Suddenly, he defined the mean to be like this, because that we've seen many times do. And then he might define the deviation to be the argument minus the mean. So that's how far away from the mean every element is. Then he might define some helper functions, small utilities like square, to be power with a preset right argument of 2, and also square root to be same thing with a half. And now, with these tools in our toolbox, we're able to write the standard deviation quite nicely. The standard deviation would be the square root of the mean of the square of the deviation. There we go. Now, since we have to have this work on an entire large array, then this is not quite going to work, because we need to revel that array first. We can easily define then our function as the standard deviation of the revel. And now if we try to, say, take this and we can concatenate it with its own column vector. So that looks like this. And then we can do f on that. We get the same standard deviation because the same number is just duplicated. That works. However, this is defining it on these small portions, and I think that's what Roger would do. We can, however, change to a more compact style where we try to integrate the various parts. So let's have a look at there's this tool called bracket defs, and we do that for f. It takes, because we have early binding, then the actual definition of standard deviation here uses all the pieces that we used to define it. We don't remember the names for them. And so this is just the corresponding formula with all the pieces put together. And we can try to see how we can make this more collected together. If you start looking here, we have the square of the deviation. We can just combine those here. In order to continue, it might be helpful to make this into a dyadic function application, which we can do by using power and commute the argument, so we can put the 2 on the left. Similarly, over here, we have the square root, and we can also put that into the parentheses here with a mean, and we can make this into a dyadic function just for symmetry by putting the 2 on the left, or we could put a half on the left and then commute. But if we want even more symmetry with what's going on over here, then we can pre-process the right argument of power with reciprocal and put a 2 instead. And now we have, again, these form in the top. We have this function here and this function over here. And since we're already having parentheses here, we can take this function and just make it an inner function over here. Well, coincidentally, if we ask Apple Card for the standard deviation, then we'll find something that is, well, identical. With a little thing extra that we are reveling in the argument before we are applying it, so it works on high rank arrays as well. Now, there's a further way that we might want to write this, and this is something I'm sure So he would have been happy with it as well. And that's using the under or dual operator. So let's define that since it's not supplied out of the box in Dialog APL. Since we're only using it here for monadic applications, we can have a fairly simple definition for it. So it's we start off by pre-processing the argument with the right operand, and then we do the main action application, and then we undo the application of the preprocessor like that. And this allows us to write the standard deviation. Call this the version that using under, and then we can write it's the mean under the square of the deviation, and then we could so this works as well. And then of course we could define in terms of that with the rebel as well. And we can have a look at what that looks like when we put it all together. Oops. Of course there's no U, it is H. And similarly, we could try to integrate things if we really wanted to, but it doesn't make so much sense here because the beautiful thing is that we're using the under, but we could. So we have this part over here. This whole thing is just a post processor on this parenthesis over here, so we can take the whole thing and put it inside. Oops. Let's try that again. Put that inside here. And now there's no point in turning the arguments around on the square, but we could replace it with, say, self-multiplication, which is another way of writing a square. And then I think it actually got it wrong here, that it's supposed to be parenthesized, otherwise this is not going to work. So we want the mean, and that done while we have the square over here. And then we undo the squaring, so that becomes the square root, and then the whole thing on the rebel. Still works. So that's it for this time. Thank you for watching.